Alright, so in this problem we have a thin, semicircular ring of mass m which is pinned to ground at end O, and we're told the bar is released from rest in the orientation shown. Given this information, we're asked to determine the angular acceleration of the ring upon release, and also the reaction force of the ring at point O upon release. Okay, so because we're looking for angular accelerations and forces, we know we're going to want to approach this problem using Newton's second law approach, and so I can go ahead and sketch a free-body diagram for this system. Now we'll note in this problem that the center of mass of a thin ring, and you can look up this geometry, in fact I want you to look up this geometry within the lecture book, but it's going to be located somewhere here at a point I'll call C. And so we'll have that the weight of the object is going to be acting there, and in this case we'll have two reactions acting at point O that I'll call OX and OY respectively. Now upon release we know that, and maybe I'll call this not C so much as G to be consistent, indicate that's the center mass. We'll also have the ability for that center mass to translate, so we can have some MAGY, some MAGX, and we also have the ability for this thing to rotate, of course, which will be I about G times alpha. So with that in mind, I can go ahead and apply my kinetics equations now. So if I sum forces in the x direction, I know that's going to equal the mass times the acceleration of the center mass in the x. And so if I do this, I'll simply get that OX is equal to m times AGX. Let's call that equation 1. If I sum moments in the y direction, that's going to equal m times AGY. And so if I do this here, what I'm going to have is OY minus mg is equal to m times AGY. And we can call that equation 2. I can sum moments about multiple points here. I could do it about the fixed point or the center of mass. In this case, let's just go ahead and do it about the center of mass. So I know in that case this is going to be I about G times alpha. And if I do this, assuming a counterclockwise positive moment calculation, I'm going to have moments, first of all, attributable to OY. And OY is going to have a moment arm associated with it of simply radius r. That will be a positive moment. And I'll have a negative moment created by OX. And let's go ahead and call this distance here D. And again, this is a distance you can look up at the table in the lecture book. And in this case, we're going to have this as minus OX times D. And that's going to equal I about G, a quantity for a semicircular ring you can look up, times alpha, and we can call that equation 3. Now if we look at these equations 1, 2, and 3, what you'll notice here is that we have currently 1, 2, 3, 4, 5 5 unknowns, but only 3 equations. So we're going to need to turn to our friend kinematics to be able to finish and solve and wrap up this problem. So how are we going to do that specifically? Well, what I would do is I'd relate the 2 points where I need to know information and have information. So in this case, I can say the acceleration of point G is equal to the acceleration of point O plus the angular acceleration of the rigid body across the position vector of G with respect to O minus omega squared times r of G with respect to O. We're told in this problem we're released from rest, so my final term here is going to go to 0. And so I can go ahead and substitute in the rest of these terms, and what I'll have is that AGX in the I plus AGY in the J, and again I'm using conventional XY notation here, is going to equal A about O, which is 0, plus alpha of this ring, which is, alpha in the K direction. I can cross that with R of G with respect to O, which is going to be minus the radius in the I minus D in the J. So if I go ahead and expand this out on the right hand side, what I'm going to have is this is equal to K cross I is going to give me J, so I'll have minus alpha R in the J. K cross J gives me minus I, so I'll have plus alpha D in the little I. If I go ahead and pull components here, in the I direction, I'm going to have that AGX is equal to alpha D, and if I look in the J direction here, I'll have that AGY is equal to minus alpha R. We can call this equation 4 and equation 5 respectively. If we look, we've added 2 new equations now without adding any additional unknowns. And so now you can solve these 5 equations and 5 unknowns to find both the reactions at point O and the angular acceleration of this object upon release. I know you got the linear algebra, so I'll leave it up to you to do. Take care, everybody. Have a good night.